Welcome. My name's George Carey. My colleague here, Will Fisher, the two of us presenting this afternoon, or part of the afternoon to the evening. Jumping right in, week two, we finished up with pump curves and system curves, and that somewhat of that relationship we're going to move forward. The first thing I thought we were going to get to last week, which you didn't, I just want to touch base at the beginning, is this thing called the B&G system sizer. And it's just been around a long time. It's a tool, a calculator. And I apologize to the people back at home. I'm just walking around the room and I have a wheel in my hand. At the end of these 4 weeks, when we send out the certificates to people that did not attend, as well as a golf shirt, we'll be mailing everybody remote a copy of or a hard copy, an actual plastic wheel, the system sizer wheel. But anyway, so it's a hydronic calculator. Over the years, the engineering community has always kind of referenced this as a pipelator, similar to like a ductilator that you'd use maybe in the air business, the air size and ductwork and stuff like that. They would call it a pipelator, but it's a useful tool specific to hydronics. So anyways, this was just a quick slide rule. This was the very first system sizer that came out back. Look at how long ago. I mean, almost 100 years ago, or whatever, 90 years ago, give or take, 85. So, and its present form today, it's a plastic wheel, comes in this sheet. It was developed by a gentleman. I mentioned the name, I think, last week. I'll certainly mention him over the next couple of weeks. He was a pretty famous engineer that worked at Bell & Gossett for a long time. All of the manuals that you guys either have in the hard binder for the in-class people, and then some of the remote would have the TEH manuals in a PDF. He basically wrote all of it. He was really known in the ASHRAE world, the engineering community across the United States, as the father of modern hydronics. He was a super genius, so to speak. And B&G was fortunate enough that he worked for them for 40 plus years. Very, very intelligent man. And he developed a lot of different things, or invented, or had patents within the hydronics industry, but just specifically tonight, right now, the system sizer. And typical kind of Gil Carlson approach, he made the wheel for himself, and he made it out of cardboard a long, long time ago. And he just made it at home, and it was just a useful tool. Everything that's on this wheel, everything that's on the app today and software, it's information that's been in charts and books for years and years and years. And he just kind of consolidated it and put it into this one spot. And it was a cardboard wheel, two-sided, and this was the original wheel. It's a picture of it. And one day, one of the marketing guys from Bell & Gossett's walking in the hallway out at B&G, and Gil's in his office. Doors open, he kind of sticks his head in, and he's sitting there, and he's got this big cardboard wheel, like a 17, 18-inch diameter wheel. And the guy sticks his head and says, Gil, what the hell you got in your hands? You know, what is that? And he explained what it was. So the marketing guy, being a marketing guy, said, hey, we should probably take this and maybe transition it to this plastic wheel, and send it out to the industry. And so that's what they did. There's tens and tens of thousands of these that have been handed out over the years to the engineering community, the contracting world, the wholesale distribution community. So anybody that's been involved with hydronics across the United States at some point has probably come across this plastic wheel. But a classic Gil, he did it for himself. He wasn't even thinking beyond that. It was just a convenient tool. It's made up of 5 scales, the wheel. And what happens is on one side, we'll call it side A, if you will, is scale 1, 2, and 3. They flip it over, and they lift scale 4 and 5. And so my thought right now is just to kind of quickly go through each scale and how to interact with the wheel. It's probably, it's pretty simple, but it's a pretty convenient device. Like everything else in the world today, there's an app for that. And so Bell & Gossett X number of years ago released an app in the Apple Store, as well as I think it's in Google Play for the Android users. And it's, I think it shows up something similar to that. In Bell and Gossett, just type in MB&G or Bell and Gossett system sizer, it populates. You can put it on your phone, your iPad. I have them on my phone, but I guess I'm of the age. I typically out in the field, I'm running around with this in my job folder, and I just would, take it out if I need to, whatever the application is, pipe sizing, guessing flows, this, that, and the other thing. But anyway, so there's an app for it as well. You don't have to use the plastic wheel. Jumping right in, scale one. Scale one just talks about the relationship that exists between BTUs, heat transfer, and flow rate. And as we discussed last week when we start looking at pumps and pump curves, flow rate is described in gallons per minute is typically how we're going to reference it. And so the scale, you have to remember that the pointer doesn't work remotely, but the scale is made up this kind of this big white, if you will, white band, if you will. And inside there is listed BTUs, the load, BTUs per hour, MBH. So it's really thousands of BTUs per hour. And then above it is a scale. They reference it as temperature difference, or you might see it as the delta T, change in temperature, temperature drop or temperature rise, but a difference in temperature. So that's the kind of the details, if you will. And then this bottom little window here where the letters GPM with a pointer. So that scale one works together. And all it's talking about is BTU per hour, delta T, and establishing or calculating or finding out what the appropriate GPM would be for that set of conditions. And all it is taking the little math formula we looked at briefly last week, and he just kind of plugged it in. And to make the scale work, that's one of the reasons why the BTUs, he used 1 MBH actually represented 1,000 BTUs an hour. The delta T scale is pretty extreme, from 1 degree all the way up to 200. That's pretty extreme for the industry, but there are some kind of crazy applications where you might get into some, relatively speaking, high delta T's. When we get into primary, secondary pumping, and we get into some design examples, sometimes you'll see 60, 80, 100 degree delta T's. So it does come into play, not an everyday thing, but it does happen. So moving forward, that's the formula behind the scenes. You can kind of, you work it frontwards and backwards, but in this case here, we're saying, hey, gallons per minute equals what's the load divided by, we talked about it last week, but the 500, typically it's 60 degree Fahrenheit water. So it has a weight of approximately 8.33 pounds. And then the flow rate is described in gallons per minute. And the load is typically in BTUs per hour. So we're taking that weight, 8.33 or 8.34 times 60. When you do the math, it's 500 times your delta T, your change in temperature. So that's the formula. You don't need a wheel. You can just sit there and plug in, but it's just a very convenient way of doing it. So temperature difference, load, either heating or cooling load in thousands of BTUs, and then again, GPM, circulation rate in gallons per minute. So just real quick, easy numbers, very low, probably not what you're typically designing around, but determine the flow rate required for 100,000 BTUs an hour at a 20 degree delta T. So all I've done is taken a screenshot and enlarged scale one. And the first thing I want to do is in that white band that lists the BTUs and MBHs is find 100,000 BTUs, which in this case would be 100 MBH. And I want to line it up opposite the design delta T, in this case 20. So 100 opposite 20. And all you do is you look down at the white small window with a GPM, and it describes it as 10 gallons a minute. So it's just doing the math. 100,000 BTUs divided by 10,000 is 10. It's as simple as that. That's what that scale one's all about. Change it. Say, hey, same load, but I'm going to design. I'm going to open up that delta T. We talked a little bit about it last week because it can influence flow rate, which means pipe size and pressure drop. But instead of designing it on 20, let's make it 40. What happens? What changes? So same thing. Scale one, line up the 100,000 BTUs, but now I'm going to line it up opposite the 40 degree delta T, and then read again in the smaller white window, the GPM, 5 gallons a minute. So whether it's 5 gallons a minute or 10 gallons a minute, they both can transfer, support, move, provide 100,000 BTUs. The difference being what's your delta T, what's your temperature drop that's going to take place between your heat exchanger, your boiler, or whatever it is that's providing the heat through your terminal units and then back to the mechanical room. One last quick one, a 600,000 BTU load at a 30-degree delta T. I don't know if I get into mentioning some applications, but we get involved with a lot of snow melting. It's one of the things that we specialize here at FIA through a couple of our manufacturers. And so it's not uncommon to design a snow melt on a walkway, driveway, big parking lot, whatever, at a little higher, a little more liberal 30-degree delta T. So in this case here, I'm saying I got a loader, maybe it's a snow melt application, 600,000 BTUs, same thing, just line it up on that 30 and then just read, you know, in this case, 40 gallons a minute. So 40 GPM will provide 600,000 BTUs if allowed that or designed around that 30-degree temperature drop. Well, I keep saying heating. Here's a quick example for cooling. Determine the flow required for 20 tons of cooling. And in this case here, we're saying, hey, we're going to design it on a 10-degree delta T or a 10-degree temperature rise. So real quickly, you would typically say, you know, per ton, when in the industry, it's kind of known that per ton, about 12,000 BTUs an hour per ton. So one quick way to calculate it would be say, hey, 20 times 12,000 is 240,000 BTUs or 240 MBH. So what I could do is I could take, again, scale 1, find the 240 MBH right here, 210, 20, 30, 40, and I'm going to line it up opposite my acceptable 10-degree temperature rise in this case, and I look at the small white window and it's about 48 gallons a minute. So on a chilled water application, 20 ton, 240,000 BTU load, 48 gallons a minute. One of the things just to point out on the wheel, let me just move backwards for a second. On that scale, down at the bottom part of that white band, you'll see GPM per ton. So he actually kind of highlighted 3 pretty common accepted temperature rises in a chilled water. And if you line them up, the 3, it's pretty close to straight across an 8-degree rise, a 10-degree rise, and a 12-degree rise. So within the chilled water world, those are pretty standard. You can design them on 8, 10, or 12. We just picked 10. 10 seems to be pretty standard, but it can move a little bit. But they just highlighted on the scale to say, hey, if you're working with chilled water, what's your temperature rise? And then you can figure out 3 gallons, 2.5, or 2 gallon a minute per ton. So real quick, you know, sometimes guys will say, hey, we keep saying the 12,000 BTUs per ton. Where did it come from? You know, years ago in the industry. And really, it's as simple as it was the amount of energy, heat, added to melt 2,000 pounds, a ton of ice. And the ice was at 32 degrees, and we melted it to 32 degrees water. So we just changed its state. We didn't change its temperature, just changing its state, a ton of 32-degree ice to 32-degree water in 24-hour period. It took 288,000 BTUs in that 24-hour period. Divided by 24 is 12,000 BTUs an hour. And that's where the industry kind of came up with that expression that started back in the infancy of cooling with ice. One last thing that sometimes the guys out in the field, whether it be us, our salesmen out in the field to help in troubleshoot or problem solve, sometimes contractors or whoever it is, but here we're out in the field and we get some real world conditions. And we're saying, hey, I've got a boiler plant. I got a leaving water temperature I can see on the gauge of 180 degrees, and it's coming back at 160. And when I look at the pressure differential gauges across a TDV, we talked about that last week, a multi-purpose valve, in this case, a triple duty valve on the discharge of the pump. So we've got some ports and we're looking at these gauges. We determined that the pump's pumping 600 gallons a minute. So all the question is at that given moment, at that snapshot, 600 GPM, 180 coming out, leaving, and 160 coming back, what's the plant load under? What is it operating at? And so all we're doing is we're kind of taking that. I mean, first of all, it's just math. We can figure it out. But if you take the scale, you kind of work backwards. We're not trying to find out the GPM. We already know it. We figured it out looking at the triple duty valve. We said, hey, we got a flow rate of 600 gallons a minute. So I'm going to line up that wheel right at 600. And then I said I had a leaving temp of 180, a return temp of 160, so 20-degree delta T. So all I want to do is find 20 up here in that delta T temperature difference scale. Read straight down, 6,000 MBH or 6 million BTUs. So I'm in that boiler room. I see those conditions. That's what's happening right now. The plant is experiencing about 6 million BTU load. Scale 2. Scale 2, nothing to do with establishing flow rates and based on BTUs and all that. Scale 2 says, once you found the information on scale 1 and you figured out what the flow rate is, what size pipe should I use? So, and again, you got to remember when this was made, which is a long time ago. But it's still, again, useful. The facts are the facts. And again, sometimes the guys will transition to the app. But it was just a useful tool, whereas today there's all kinds of software, like I said, that you guys are probably going to reference on a day-to-day basis. But Scale 2 references 2 types of pipe, Type L copper tubing and Schedule 40 steel pipe. There's 2 terms that they're going to use, milli-inches per foot and then feet per 100 feet. The milli-inches comes from days gone by, years and years ago. We're never using that. You're never going to see it today, at least in calculating head loss, friction loss, and a closed loop system. But years and years, when the industry was transitioning from gravity hot water to pumped forced circulation, the pipe sizing was tremendously big, and it had to be for gravity hot water. There was no circulator. Once they started transitioning and adding a circulator or booster pump, when you were using this existing technically oversized piping, the pressure drop was so low that to have some kind of numbers that made a little bit of sense is they incorporated this milli-inch. It's long gone. It's just there mostly for historical reference. Right here at the very bottom, feet per 100 feet, that's what we're going to reference. That's what we use. We talked about it last week when you look at pump curves. They're listed in feet of head per 100 feet. And so you look at Scale 2, pipe size, friction loss rate. So we're trying to establish what size pipe, whether it be Type L copper or iron pipe, in this white band here is the flow rate, is listed in gallons per minute. And that top scale, this top side of it is saying, hey, this is the friction loss, the piping friction loss in feet per 100 feet of pipe. So anyways, it's just an enlarged view of it, if you will. Again, pretty low numbers, but they actually kind of correlate to what we just figured out on Scale 1 with some flow rates. But in this case here, this example is saying, determine the pipe size for 10 gallons a minute in a hydronic system. So the way I approach it, or the way you would use the wheel if you so chose to use it, is you'd be down on Scale 2, and in this white triangle, this white band, I want to try to find the flow rate that we're looking for. So in this example here, we're saying 10 gallons a minute is right here, somewhere in that white band. And if I'm going to say I'm solving for copper pipe for this example, what I want to do is I want to line up the particular pipe size that I'm going to select. I can't just have it, off of this pointer here. It's got to be lined up exactly. So in this example here, 10 gallons a minute kind of falls within that white band. It's kind of a good industry standard in terms of selection. I line up the copper, and all it's going to tell me is the pressure drop. So in this case here, 10 gallons a minute flowing through 1¼ inch copper pipe is going to offer 2.6 feet of frictional resistance for every 100 feet of pipe. It's as simple as that. In that previous example, we said 100,000 BTUs at that 40-degree delta T. So we increased the delta T, which cut our flow rate in half, in this case, 5. So again, what size pipe? I'm only pumping 5 GPM now. I find it in this white band. The first pipe size that I come across that kind of meets that criteria is 1 inch copper. So same thing, just read it. Okay, It's telling me that flow rate of 5 GPM through that 1-inch pipe will create offer 1.9 feet of pressure drop in feet of head for every 100 feet of pipe. So another quick example. What size pipe do I need for 70 gallons a minute in a typical hydronic system? So as you take the wheel on scale 2 and you're kind of scrolling through and you're saying, hey, where's 70 GPM? And typically speaking, the desire is to not spend too much money. So I don't need to necessarily oversize the piping because I'm going to be buying more expensive pipe and more expensive fittings. And then I don't want to go on the other side and undersize the pipe and create some real excessive either pressure drop and or velocity. So I'm trying to find that mid-range. So as I scroll through scale 2 and I'm moving the flow rate and I'm lining it up opposite various size pipe, the first pipe that I come across, in this case here for iron pipe, is going to be 2.5-inch iron pipe. And that's 70 gallons a minute, falls right here to the left-hand side of that white band. So I could just look at it, read it, and it says, hey, for every 100 feet of pipe, that 70 gallons a minute through that 2.5-inch pipe is about 3.5 feet of frictional resistance. So I got 100 feet, 3.5. I got 200 at 7 feet, etc. And this is one of those examples where you might actually have two answers. So in this case here, 2.5-inch, a little higher pressure drop, but still it's acceptable. But as I move that scale and that wheel on scale 2, I also see that 3-inch pipe, iron pipe size, and that 70 continues to kind of fall within that triangle. It's just obviously to the right-hand side. And so when I look at it, it's telling me it's only offering or creating about 1.2 feet of pressure drop for every 100 feet, which makes sense. Same flow rate, 70 through a certain diameter or a little bigger. One's going to have a little more resistance. So sometimes one of the things, and a lot of the charts that or software that you guys are referencing will kind of account for this. Upfront cost, that 2.5-inch pipe and fittings, probably less money from the distributor, from the wholesaler installed. The 3-inch is going to be a little bit more. How much energy is being consumed per year? Times 10 years, times 20 years, life of the system. So operating costs and all of that comes into play. So sometimes the criteria might not just be, hey, spend the least amount of money up front. It might be, what's my overall scope? What's my overall desire? What's to do the client the best service? There's all different little factors. So just be aware that sometimes a couple different pipe sizes might make sense. And some of the charts that ASHRAE will publish, and I think we even had it at the end of the last session's presentation in the PDF form, they talked about hours of operation, less than 2,000, 2,000 to 4,000, whatever. You might get into bigger pipe because you're running for longer, you're consuming more energy, use a larger diameter pipe. Yes, more expensive up front. Overall operating costs might be more favorable, if you will. Scale 3 talks about right here, establishes the water velocity in feet per second. It's the one and only time where the scales actually work together. So like I said, on scale 1, you figure out your flow rate based on BTUs, delta T. When you go down to scale 2, you're not working together. But this one example, scale 2 and 3 work together. So whatever we find in 2, we don't move it. We just kind of glance down and start looking at 3. Couple of quick just rules of thumb. Water velocity should be high enough to carry any type of air bubble, small little entrained air that might be out in the system. We want to have a minimum velocity, typically 1.5, 2 feet. We don't want to typically get below that for air movement or air flow, if you will. On the high side, velocity, maximum velocities. And this will vary, but if you're doing a closed loop hydronic system, chilled water heating, and noise is a concern, a classroom, an office, a home, an apartment complex, a hospital, where there's people in these various rooms and noise is, an element you want to be aware of, there's a certain max that you want to abide by. You get into commercial settings, manufacturing, where there are other noises. And so noise isn't your concern. It's just, hey, I just don't want to erode the pipe by over my velocity being too high, and I kind of erosion through a corrosion. So I'll have a high side. So where noises are concerned, they in the scale here, they say 2 inch, but it actually can apply to larger diameter pipe. It's more the application. Typically, you don't want to be beyond 4 to 5 feet per second on the high side for noise. For larger pipe and or just more of a commercial setting where there are other noises, so noise is off the table as a concern, typically, you know, around 8 feet or so per second. So real quickly, just looking at scale 3, it's right here. It's right below scale 2. So it does work. This is the one time, like I said, where the two scales kind of work together. So find the velocity at 10 GPM flowing in that 1¼ inch copper pipe. So up here in scale 2, I had 1¼ inch lined up. I saw the 10. All I'm going to do now is I'm going to glance down to scale 3, and I want to find on this scale, in this case here, the GPM is in that white band. Where does that 10 intersect the velocity feet per second scale? And it's just about 2.3, 2.4 feet per second. So fast enough, not too fast. Good selection. Just a confirmation. You figured it out up above on scale 1. You find your pipe size on scale 2. You glance down at 3. Hey, am I in the ballpark? Am I not too fast, not too slow? Good. Keep moving forward. And again, 5 gallons a minute, same thing. Just glance down, see the velocity. Fine. 1.8. Here's a quick question. What's the velocity of 1,600 gallons a minute moving through 8-inch pipe, 8-inch steel pipe? So what am I going to do? I'm going to go to scale 2, and I'm going to line up 8-inch pipe. And then I'm going to look down to scale 3, and I want to find the flow rate of 1,600 gallons a minute. So here's my 1,500 gallons a minute. There's my 2,000. So somewhere in between, obviously closer to the 15, I'm going to see where it intersects. And it's probably close to or about 10 feet per second. Kind of more than or what the industry standards would say, hey, try to keep it below 8 or less. So they might say, let's pick another size pipe. So the next pipe size up becomes 10-inch. So what's the velocity of that same flow through 10-inch pipe? And again, same exercise, 1,600 GPM. Where does it intersect? You know, just about 6 feet, plus or minus 6 feet. It's good selection. So again, just a way of using scale 3. The last one, go through real quick, scale 4. And you got to remember again, when it was developed, there were no calculators. This is back in the early 60s when this first came on the market. So there, you know, every day, I mean, everyone today on their phone has a calculator. Never mind what you would have for calculators in school and all of that. But years and years ago, that calculator didn't exist. So it was just a calculator. That's all scale 4 is. And all I'm saying here is whatever you figured on scale 2, because that was based on what? The pressure drop of a certain flow rates through a certain size pipe for 100 feet. Scale 4 says, how many feet do you have? 50, 5,000? What's your length of run? And it would do the calculation for you. To me, of the 5 scales, it's the most useless relative to how we operate today. But back in the day, it was part of the 5 scales. One other comment, real quickly. To use scale 4, first you have to calculate the total equivalent length, or the TEL, of that circuit. And all they're referencing is that fittings can offer, and we kind of touched on it last week a little bit, but fittings will offer a little more resistance than straight pipe. They'll actually have an equivalent how many feet of TEL relative to if I was a straight piece of pipe. Out in the field, to be quite honest with you guys, engineering, you're designing, you're responsible from the very beginning, you're going to be a lot more accurate. What they're talking about here is there is a rule of thumb. Sometimes when you're out in the field and you're trying to help a guy, maybe either size, resize, there's a little bit, there's been an addition added, whatever the case may be. but you can't find all the pipe. It's existing. Some of it's behind the walls. So you kind of do what they call a swag method. And that's a scientific wild ass guess. But you can say, hey, the length of the building, I can figure out the straight run of pipe. How many fittings are there? I can't find it, or I can't see it, or whatever the case may be. So a rule of thumb that was accepted, probably a little safer than it needs to be, was whatever that length of run is, add 50%. So if I had a 300-foot run, 50% would be 150 of that. So I'd say I have a TEL of 450. And that's just to account for the fittings that I can't find, but it's to account for that total pressure drop that could occur. So anyways, on the jacket, those that are online, remote, when you receive the system sizer in the mail with your shirt and certificate, there'll be a sleeve. And on that sleeve, the backside, and again, was useful years ago, but they were just showing an example of different fittings that would have been used back in the day, and whether they were steel or cast iron, screwed or flanged. But just a quick example, we're saying, hey, what's the equivalent length of straight run if I had a 4-inch cast iron 90-degree elbow? That's all it's saying right there. It's equal to 11 feet of pipe. So I had a bunch of them. I have to account for that. If I can't find them, maybe I just use, yes, sir. I don't know, to be quite honest with you, the exact. I'd say that probably, I mean, it's not, this is all published from like the fitting manufacturers when they're doing their testing as to what that pressure drop is. With that ASHRAE K factor, is it doing the same thing, saying it's assigning a TEL for a fitting? Is that what you... Oh, okay. Oh, you're probably a little more accurate than this thing. Yeah, I would say that's more accurate. Yes, absolutely. Which in a world where you're designing and specifying and creating the system, you're staying in that world. More accuracy. This is back to that, what they would reference in the industry, kind of a rule of thumb for that 50% factor. The chart's a little more accurate than that, you know, because manufacturers tested it, but I'm thinking that K factor is probably even a little more fine-tuned than what this was from, you know, years back. Sure. So just, again, it's just a silly little example, but what we're saying here is what we found from scale 2 before is we needed 1.25 inch pipe for 10 gallons a minute flowing through copper pipe. And in the example, they said, hey, we've got actually 200 feet of pipe in this building for this example for 100,000 BTUs. So to use scale 4, they'd say, hey, well, you get 200 feet, but you got to account for the fittings. So I'm going to use that rule of thumb in this case. So I'm going to add 50%. So I'm going to say I have a TEL of 300 feet. And all you do on that scale 4 is you'd find the 300 feet, and you're going to line it up opposite the pressure drop that we established, which in this case here, back up, for 1.25 inches, we said was 300 feet was what? Just about 2.6, I think it was, per 100 feet. And then I say, hey, line it up opposite 300 feet is my total. Read straight down here in this small window where it says total pressure drop. And it's just over 7.5, just under 8 feet. Again, it's just math. It's a convenient calculator, not needed nowadays the way it was years ago. Same thing that holds true on that scale 2. We're saying, hey, what's the TEL for 130 feet with a flow rate of 200 gallons a minute? What size pipe? 4-inch. Okay. 200 GPM is about 2.2, 2.3 feet per 100. 2.3, we'll call it. Now I flip it over, go to scale 4 and say, hey, what's my total? TEL is 130. So I'm just going to find 130 in the scale here, 100, 110, 120, 130. Opposite, about 2.3, read straight down. It's just a calculator. And it's saying it'd be 3 feet of pressure drop. Scale 5. Scale 5 is what we're going to kind of focus on a lot tonight, because that's having to do with, as we get into system curves again, and we get into pump affinity laws and how that all plays out. Scale 5 is that relationship that exists between the change in flow and the change in head, and that corresponding difference. So the head is kind of a basic statement. The head varies approximately as the square of the change in flow. And we'll go through a couple of examples here. But what we're saying is, when he built that scale for himself, he basically, when he's lining up these various numbers, it's based on this little formula here. As I change the flow, that change, whatever that answer is, square it times your original pressure drop, and that becomes your new pressure drop. I'll highlight it, and we'll touch on it a little bit in a couple of minutes. But you'll see the letters C sub V, or valve coefficient. We'll talk about that because that kind of ties in with the valve industry, valve manufacturers, and their known pressure drops and how we can take advantage of that. So, real quick example, I got a chiller, and the chiller manufacturer says, hey, when you move 100 GPM through my chiller barrel, I've got a pressure drop of 12 feet of head loss. And the question is, hey, if I want to increase that flow, that load through that chiller, what's the new pressure drop going to be? If I'm moving from 100 GPM to 150, can I calculate it? And the answer is yes, you can. Or quite simply, you can just take that scale, either on your app, on your phone, or the wheel itself. And what you're going to do is say, hey, what's the known? What two pieces of information are accurate? Well, one is the flow rate. That's in the white band on scale 5. GPM, it's listed right here on either side. And then the pressure drop. So in this case here, on the top side of that scale, it's listed in feet of head. You'll notice on the bottom, we reference it in PSI, pounds per square inch. But in this example, where the chiller manufacturer says, hey, I got 12 feet of head loss, just line those two numbers up, 100 opposite 12 feet. Without moving that scale, now just go find the new flow rate. So in this case here, 150 GPM, and read straight up. And that becomes your new pressure drop, about 27 feet ahead. So 100 GPM, 12 feet ahead, bump it up to 150. The relationship, that squared relationship, that flow, that pressure drop will now be about 27 feet ahead. It's just a quick example of, once there's a one known flow and head calculation that's accurate, you can figure out any change in flow and what that change in pressure drop will be. Plot a system curve that has a flow rate of 200 gallons a minute and a head loss of 30 feet. So what we're saying here is, if I took that scale and I said, hey, what's my known conditions? Start with this. You did a calculation and you said, hey, I need a 200,000 BTUs. I need 200 gallons a minute, whatever the case may be. And in that system where I'm moving that flow rate, required flow rate, I'm going to have a pressure drop of about 30 feet ahead. So that's a known. That's accurate. You've calculated it. To build a system curve, you can really just arbitrarily pick other flow rates. And what you do is, once you're on scale 5, line the two known conditions, and then 100 GPM, read straight up, 7.5. 150 gallons a minute, just about what? 17, 10, 15, 16, 17 feet ahead. 300 gallons a minute, read straight up, 65, 60, 70, so about 67 feet. So then what would happen is, again, years ago, today, software does it for us automatically. It's all, instantaneous. But you would plot a curve, and you'd put those numbers down and create the system curve. And where that curve intersects, ideally, is where you want that pump to be operating. That's the conditions you created, 200 at 30 feet ahead. So you can use scale 5 to establish that system curve. Kind of a common application, and it's in the engineering manuals, and it's part of the PDFs of the TEHs, but one manual is very specific to parallel pumping. We're not going to spend a tremendous amount of time, but it's just a quick example of, when you're doing parallel pumping, you got to kind of cover your bases. You got to make sure that everything's going to work when both pumps are running. And then what happens when one pump shuts off, either fails or intentionally is turned off? What changes? And will the remaining pump function properly? Will it work? So it's another way of using scale 5 in the system curve. But when you're doing pumps in parallel real quickly, what we're trying to highlight here or show is this is my design condition right out here. So my design flow rate is this, A. But I'm picking 2 smaller pumps. And each pump will give me half of the desired flow rate, but at the necessary calculated head loss. So each pump can give me half the flow at the design head loss. And when I put them in parallel, and they're running in parallel together, they will give me double the flow, the appropriate flow rate that I was chasing after at that design head loss. So pumps in parallel, each one gives you half the flow at the total head, put them together, and they'll give you that. Now the pipe sizing is sized to the total flow, right? You got to start with that. You have to understand that I'm not sizing it for one pump. I'm sizing it for 2 pumps working together to that desired flow rate. So again, there's that system curve formula, or just use scale 5. And what we want to do, what we want to make sure, and again, software today does it for us automatically. Whenever you guys get involved with selecting parallel pumps, they're going to build a system curve. And what we want to know is, okay, each pump operates at B, double it. Here's my combined operating point. What happens when only one pump's running? Where does it operate? Because sometimes the first instincts would be, hey, if I pick 2 pumps at 500 gallons a minute each, so I get my 1,000, and then one pump's off for whatever reason, it's not working, someone intentionally shut it off, loads light, I'm going back to the 500 gallons a minute. But I can't, because the pipe size is there for 1,000 gallons a minute. So I don't have the resistance to stay at 500 at that head loss. So I'm going to operate further out to the right of that curve, and I'm going to intersect the system curve of that 1,000 gallons a minute at whatever that head loss was when both pumps are running. So in this case here, it's saying, hey, I'm going to intersect at point C for single pump operation, which is sometimes can be beneficial because the percentage isn't 50%. It could be 70, 75, 80% with single pump operation. So it's something to be aware of. Here's a real simple, quick example. The conditions are, I need, say, 1,200,000 BTUs for a heating application. And that's where I got the 120. I designed it on a 20-degree delta T. And when I did my calculation, I got about 35 feet of head loss to overcome to get that appropriate flow out to the building. And I'm looking at, say some stock pumps, wholesaler, rep, whatever. Obviously, in this example, nothing falls with the conditions that I want. But hey, I got 2 smaller pumps, and if I put them in parallel, I can get you there. I can get 2 smaller pumps. So what do I look at? I say, okay, I'm looking for 120 at 35 feet ahead. Half of 120 is 60. Oddly enough, I have a curve, pump B we'll call it, that can create or deliver 60 gallons a minute and overcome 35 feet ahead. So I'll pick 2 of those. So I'll build a parallel curve. So all I'm doing is taking that 60 and doubling it. And all the way along, and again, software does it for us automatically, but here's my design conditions and here's the operating point when both pumps are running. And then the last part of that equation would be, okay, great, I've met my conditions. 1 pump is running. What happens? So to know that, I build that system curve. And again, that's going to happen on your computers, on your software. But for you, you just want to know when I'm looking at that, what is that line? Oh, that's a system curve. What's it based on? 120 at 35. So you know that. So then it says, okay, where am I operating with 1 pump? Well, it's right here. When I look at the flow rate, it's about 90 gallons a minute. That's not 120 and it's not 60, but it's about 75%. So it's just to be aware of that. You can get by with, sometimes the guys will design parallel pumping for different reasons. Recognize that when 1 pump shuts off, it can't back up to half. It's going to be something greater than half, but it's not full 120 because it can't be. If that was the case, you would have had one pump. So it's just another example. One last thing on scale 5. You can be used to select control valves. And what we're saying here is manufacturers, when they manufacture their valves, there's an orifice. And it could be a fluctuating orifice. It could be different ports, full port, reduced port, et cetera, standard port. But they have a rating. And they rate it in this thing called a CV, C sub V rating. And whenever you look at a published information submittal, whatever, of a valve, and it lists the CV, what it's telling you is this. That CV, that valve was tested. So the flow across the valve stated in GPM that creates a 1 pound pressure drop across that valve. That becomes that manufacturer, that valve's CV rating, C sub V rating. So if I have a rating of 50 on a particular valve, what it's saying is the manufacturer tested it and I had to move 50 gallons a minute through the orifice to create a 1 pound pressure drop. And that becomes, bang, that's a CV. 50 gallons a minute, 1 pound pressure drop. Picture speaks 1,000 words. Here's a valve. I have an inlet pressure. I have an outlet pressure. Whatever flow rate is required to create that 1 pound pressure drop. Or when you look at scale 5 and you're looking at, and you say, hey, 1 PSI on the scale 5 curve is lined up opposite the letters C sub V. Straight up, if you convert it and we're dealing with basic water, the equivalent would be 2.3 feet ahead. You can have 1 pound pressure drop or 2.3 feet ahead. So all of a sudden you can start using that valve to establish flow rates. You know the pressure drop. Yes, sir. Well, it would actually be lower, right? Meaning my inlet pressure, and it's not like 1 jumping up to 2. It's saying, here's my inlet pressure, and I'm going to be 1 pound lower. I've had a pressure drop of 1 PSI, and they want to measure what was the flow rate through the valve to cause that 1 pound pressure drop. Yes, yeah, that if you want to call high and low, inlet high, outlet low. Okay, yeah. And really what it is the manufacturer, he's testing. And what happens, I guess, again, next picture, how they test the valves. Water level remains constant right here on the left-hand side of 2.3 feet, or maintaining that 1 pound inlet pressure. Pressure at the valve outlet is 0. It's dropping into a container that's going to measure that amount of water. The volume of water flowing for 1 minute can be weighed to determine the gallons per minute. That becomes that valve manufacturer, whether it's Honeywell, Siemens, Johnson, Powell, any of the valve manufacturers, they all have a C sub V rating. They test the flow through an orifice to say, I know what this valve capacity. And some of the reasons, and you kind of get into the weeds real quickly, and we don't want to tonight, but you can have like 2 valves that are both, say, 2.5 inch in pipe size, but they could have internal orifices that are different. And one could be less expensive and one could be more expensive. And you start looking at the CV, and one's got a lower number, one's got a higher number. Well, the lower number is what? A lower number meaning lower GPM. So the orifice is smaller to create that 1 pound pressure drop. So if I'm trying to move more GPM through that smaller hole, I'm eating up more energy. If I have a valve that has a higher CV, that means more GPM had to go through that valve to create that 1 pound. So depending upon your application, sometimes you want a lot of pressure drop, and that's called control valve authority. I want to really regulate the output of something by controlling the flow. I want to create good pressure drop. Other times it's almost in the way, it's an open or closed, So I want low pressure drop, so I don't want to eat up all my pump head just on the silly little valve. So it's just understanding that dynamic, that relationship that exists. And it all comes back to this relationship of what's the flow in GPM causes a 1 pound pressure drop. That's that particular valve manufacturer's PV rating. So a real quick example of how you might state it or might use it. A control valve is to be selected to cause a 3 psi differential. Say it's a control valve on a chilled water coil. And the chilled water coil is supposed to, now we're getting, again, back to the weeds, 2.9 GPM through that coil. So the control valve selected to cause a 3 pound pressure drop when there's 2.9 gallons a minute going through that valve. So you work backwards and say, hey, what's the CV rating of the valve that I should select so that when it sees that condition of 2.9, it will create that 3 pound pressure drop I'm chasing after to have maybe some good control valve authority. So I could do the math, or I could just grab scale 5 real quickly on my iPad or my plastic wheel, and I'll say, hey, what do I know? What am I chasing after? I want 3 pound pressure drop at a flow rate of what? 2.9 gallons a minute, right? So there's my 3 PSI here. The bottom side of that scale 5 is in PSI. So 3 PSI, which is what I'm chasing. My flow rate, I said, was established to be 2.9 gallons a minute. So 2 gallons a minute, 3 gallons a minute, 10th increments. So 2.9, line those two. Now, and you'll notice, and I mentioned it earlier, in scale 5, you have the letters CV. What are they lined up opposite? Well, on the bottom scale in PSI, it's lined up opposite the number 1 pound pressure drop. On the feet of head scale, it's the 2.3 feet of head. So they line up opposite each other. So what I want to do is, this is my known condition, 3 PSI pressure drop at a flow rate of 2.9. Read back. What CV should I be selecting? What flow rate in gallons per minute, because that's what this white band indicates, is the flow rate, will cause a 1 pound pressure drop, so that when I put it into a set of conditions where they want 3 pounds, this is the required flow rate. So right here, I have a CV. When I look up the specs on that Honeywell valve or that whoever, Johnson, Siemens, if I get a valve that has a CV of 1.7, and I have the fitter put it into that system with that coil, that chilled water coil, that has a flow rate of 2.9 because the balancing valve guy tested it and knows it's 2.9, I'm going to have a pressure drop of about 3 pounds across that valve. I'm going to have real good control valve authority. So again, a little bit in the weeds, but again, it's just simply scale 5. It's that relationship of flow and head. And it kind of works. If you get nothing, if you get that, that's big throughout your career as far as in hydronics and designing and selecting. So no questions, I assume. Moving right along. Do you have a question? I'm sorry, I shouldn't assume anything. Let's see, let's get out of that. Okay. And now I want to find variable speed. And I want to share. What do I want to share? Share. I don't see it. I'm hiding it, and I don't want to hide it. Share screen. Not letting me. Oh, am I not seeing that? Oh, there it is right there. Yeah, God almighty. Behind this. So I want to jump into the subject of variable speed pumping. It's all day, every day. You guys are involved as you progress. You're already probably doing it in your careers, but variable speed pumping is very, very common. Just do a little bit of a history real quick. Why we do it and how it came to be, and then some of the different options that are out there. The technology is constantly evolving in the right direction, becoming more effective, more efficient, more accurate. But just real quickly, why variable speed? So as systems grew, this is some of the pictures I'm going to show right now in this PowerPoint, would have been out of some of the TEH manuals that you guys received, both in the manual and then what you'll see on the in the Dropbox on the PDF version. But what they're saying here is I have a chiller plant, and then I have some closely spaced tees, relatively speaking. I have primary, secondary piping over here, where the chillers are inserted, if you will, into the distribution system. So I have a secondary pump that's now feeding terminal units. And these terminal units are controlled, in this case, by two-way valves. And again, this, before variable speed, it was constant speed. That was the option. You had a constant speed pump that you selected for design parameters, design conditions, flow and head, and then you had control out to the terminal units, thermostat, discharge air temperature, whatever it was, typically a thermostat, space temperature, that would either modulate a valve or open close, either or some mixture thereof. And one of the challenges would be is if you were under design load conditions all the time, we wouldn't have this conversation and we wouldn't have variable speed pumping and there'd be none of this. But the reality is you have design conditions that exist for 2, 3, 4%, 5% of the season, whether it be chilled water or heating on the heating side, and then something less than. So we have valve operation, valves opening and closing. And so what this is, again, an older chart, but it's saying a pump curve. And it's saying, as a quick example, here's my design conditions. I need 1,100 gallons a minute at 100 feet of head loss for this big campus distribution system, this big, whatever it is, big apartment complex, big hospital, whatever. And when all the valves are open and everything's running and everything's calling, everything's fine. And I might have a control valve pressure drop of 20 feet. And that's a little bit about what we just discussed on sizing those control valves with a CV, trying to create some control valve authority, is I want a valve that can control at each terminal unit. So I'll pick one of those 50, 100, 20, whatever the number of terminal units I have, I'll have a control valve head loss. And so when everything's open and everything's running, I'm at my full design flow of, say, 1,100 gallons a minute. This is like what they would refer to as the flow head loss curve, and that's based on equipment, piping, terminals, balance valves, all right here. This 20 feet of control valve or control head loss is fixed. That's a fixed number. That's not changing, the 20 feet. But the other 80 feet is variable. At design flow, that's what it is. 80 feet plus the control head of 20 for a total pump head of 100. As the valves close, the pump moves which way? It moves to the left. It backs up on its curve because there are less ports, less terminals open, so it backs up on its curve. What happens to the control valve is you're developing this high head, and all of a sudden this valve's responsible for eating up that really excessive pressure drop. In this case here, at about 50%, 550 gallons a minute, instead of the original design of 1,100, I might be eating up as much as the head absorbing by the control valve is 90 feet. Very excessive. What they did is, this is at the beginning, as systems were being built and designed and installed, and then they say, hey, we're experiencing some issues here, some system conditions that we didn't really recognize or think about initially. Just another quick example, but maybe related to, a little more modern today, but it's saying system pressures in a constant speed. That's the key, constant speed pumping. So if someone was to put gauges around the system, and you're saying, hey, I'm pumping, in this case here, for easy numbers, 100 GPM, and I'm overcoming 100 feet of pressure drop. And then I just assign different pressure drops for whether it be terminal units or piping, coils, what the pressure drop is, control valve, what the pressure drop is, more piping. And I come back to my suction of my pump, and I still have my, say, my control head of 20 feet. I'm adding 100 feet of pump head. So I'm suction 20, discharge 120. So that's a kind of a stated set of conditions. And what I'm going to do here is I'm going to highlight a pump curve that, maybe got selected with some pump software that says, hey, 100 GPM at 100 feet ahead. Here it is. 3450 RPM constant speed pump is what I selected. These are pretty unusual conditions, 100 at 100, but it's just an example to run with, just to work with. And what we're trying to show here is, as the system conditions change, the valves close, not all of them, but to the point where I have 50% of that design flow. In this case, my pump is now back down to 50 gallons a minute. But in that constant speed application, look at the pump head. It's actually climbed. It's climbed to 115 feet ahead. Why? Because it's backing up on that curve. Here's my 100 GPM at 100 feet ahead. As I start backing up on the curve, down here in the middle here, where I'm trying to circle with this arrow, it says 50 GPM. So 50 GPM, where it intersects that pump impeller curve, which is where it has to operate. The pump has to operate on that curve. It's developing about 115 feet of head. That's all we're stating here, is when it's full flow, it's 100 gallons a minute, 100 feet ahead. I back up, valves close. I'm at 50% of flow. I develop a higher head, 115 feet. Same phenomenon's taking place. Look at this pressure drop across this, what this control valve has to absorb, 92 feet. But I got a quick question for you here. When I look at the design conditions and I see the pressure drop that's been calculated, and you guys did the calculation a while back, and this is what you come up with on your plan. And all of a sudden, you're saying, hey, when real world conditions exist and I have pot load conditions, in this case, say 50% of flow, 50 gallons a minute, I can assign different pressure drops because those pressure drops are real. They're going to change. Why? How do I know those numbers are right? Where do they come from? Let's do a quick example together. And for those that are at home, I apologize for not having the wheel in front of you, but real quickly, this one circuit, which is supposed to represent a system, we're saying I'm pumping 100 GPM. And through this section of piping, maybe it's a terminal unit piping, whatever, it offers 30 feet of resistance. When I decrease the flow to 50, and why am I doing 50? Pot load, valves closed. So I can take scale 5, or I can just do a calculation, or I can get on my app. But I could say when I was pumping 100 GPM, I was creating or was experiencing a 30 feet of head loss. So scale 5, 100 GPM, opposite 30 feet ahead. And then all of a sudden, on scale 5, without moving the wheel, or if I was doing a little math calculation, now all of a sudden I have 50 GPM going through that same network. And I look and I say 50 GPM is 7.5 feet of head loss on scale 5. Huh, that's what it's listed here. Same thing on the coil. When I had my full flow, 100 GPM, I had a 10-foot head loss. When I cut that flow, so again, scale 5, 100 opposite 10, go down to 50, there it is, 2.5 feet of head loss. So that's very real. That's happening. You reduce your flow, you reduce your head loss. But you still have this constant speed. We haven't introduced variable yet. And this is the reason why we went to variable, why the industry was desperately trying to get there back a while back, is now all of a sudden that control valve that had 10 feet of head loss is now responsible absorbing 90 feet, 92.5 feet of head loss. That's excessive. That's real velocity or maybe erosion. It's necessary. It's what we need to do, but that's the limitation, as well as waste perhaps of some energy with constant speed. So that's what would happen. As you backed up on the curve, because you have to operate, that pump has to operate somewhere on that stated 5.2-inch impeller diameter. Why? Because you designed it, you selected it for this set of conditions, 100 at 100. When you have the pot load, you're moving. Not variable, it's fixed. This is what happens in the system. So then the industry said, hey, how can we get away from that? Again, before variable speed, how can we move away from that? So one of the first answers was, what did they change here in the drawing? Yeah, we went from 2-way to 3-way. What's the benefit of that? Which gets us what? If you bypass? Constant flow. So you're not experiencing that movement backing up on the curve. Downside, you see it right here stated, and it's, it's Mother Nature, it's a fact, pump power waste. It got you from that phenomenon of having this 2-way valve, seeing all this pressure drop because it's backing up on its curve. What's the purpose of these black bypass balance valves? Well, that can be the piping itself is your bypass. You're absolutely right. And it's a bypass balance valve. And the question is, why is it needed? Or the same pressure drop as the terminal unit. And what's going on here is, if this port right here, where this arrow is, was closed, so all the flow is going through the terminal unit, there's a certain pressure drop. We calculate, we figure it out. If I say, hey, discharge temperature, space temperature, whatever, the thermostat says, hey, close the valve, close the 3-way valve. So now this port's closed, the bypass is open. And I want to achieve that, still that kind of constant flow so the pump doesn't move up and down on this constant speed curve. It'll go to bypass. Well, that piping right here by itself is not the same resistance as the coil, the terminal unit. So the fitter, the pipe fitter, but it starts with the engineering community, would establish and said, hey, when that goes from either coil or bypass, the pump doesn't want to see a change. I don't want to see a change. Because if I do, what am I going to do? If I have a lower pressure drop, the curve is shifting way out to the right. Now I'm going to over pump, waste of energy, more energy being wasted. So at least I want to balance the bypass piping to simulate pressure drop the same as if it was going through the terminal. So there's no change. So that's what they would do. Now, it would get you it would take away some of the issues that you experience with this 2-way valve, with this control valve, seeing this really excessive buildup in pressure. But as it states here, waste of energy. You might see it today, not so much, because to be honest with you, at some point, they actually ASHRAE and energy, I think it's ASHRAE 90.1, which is X number of years old. They were really saying, this is such a waste of energy. We want you to plug that bypass port. If you're not going to change the valve and take it out and make it a 2-way, as they introduced variable speed, they wanted you to at least plug that bypass port. But anyways, that's a kind of a modern version of that same older drawing. real quickly, this is just kind of a highlight, if you will, or an exploded view of what's going on that bypass with that three-way valve. And it could be, most likely it was a modulating valve, which would mean what? What's the modulating valve mean as opposed to, say, a two-position three-way valve? Two-position would be, I'm either, in this case here, 100% open to the coil, so blue to blue, red indicating closed, so all the flow's going through my coil. And if I went to the extreme the other way, the red is closed from the outlet of the terminal, so I have no flow through the terminal. All of it's going through my bypass pipe. Here's my balance valve to simulate that terminal pressure drop. So you might call it a bypass valve or a diverting valve. The term almost doesn't matter. It's semantics. But the point was, I'm taking flow and I'm either putting it through the coil or I'm putting it through the bypass, or a lot of times it'd be somewhere in between. I'm either bypassing a portion, if I'm throttling, 50% through the bypass, 50 through. So even then, you think about it, that changes the pressure drop. So all of a sudden, the pump can still start to slide out on its curve because the resistance change. If you're putting all the flow through the coil, there's a certain pressure drop. Putting all the flow through that balance valve, there's a pressure drop. You split it, there's actually less pressure drop through each, and the pump can move out to the right. But it was the way, it was the industry evolving. They weren't there yet, but they were getting there. So another example would again be that two-way valve, but they said, hey, we can't have all of these units with two-way valves, so they might add three-way valves to get that flow, that bypass flow rate. So that as the valves close, why would they close? Because the space temperature was satisfied, heating or cooling. And they would do their thing, again, with a constant speed pump at the time, they would have at least this bypass, this three-way valve to provide an outlet. So what would happen, again, just real quickly, if I'm dealing with two-way valves, they can be very simple. It could be on-off, or it could be, and a lot of times, most likely modulating, where it would just fluctuate, depending upon, feedback from the indoor air temperature or space temperature and its area that it's controlling. But again, 100% flow, blue, 100% no flow or shut off, I should say, 100% closed, the red, or somewhere in between. One of the interesting things to think about is, how does pressure drop change as flow rate changes? Well, we've kind of talked about that already. That's that scale 5, or that relationship between flow and head. You can actually figure out what the relationship is. As the flow reduces, the pressure drop reduces. That's that squared relationship. I don't have a calculator in front of me, but all we're saying here is whatever the percentage of flow rate is, if it's 100% flow, the pressure drop's 100%. If I reduce the flow in half, right, and that changed from 50 or 100 down to 50 gallons a minute, and I squared it, and I times it by the original 100-pound or 100-foot pressure drop, it'd only be a quarter of that. It'd be 25%, or anywhere in between. So if I have this modulating valve, I have modulating pressure drops because I have reduction or increase in flow. But that's changing all the time with these two-way valves. And that applies to that variable speed that we're going to get into as those system conditions are changing. So in reality, you have a system curve. Well, you have multiple system curves, actually. And they change depending upon where the flow is. Is it 100% design conditions? Okay, here it is. Is it 25% closed, only 75% flow? Here's my new system curve within that constant speed application. And it's just continually changed. But it would constantly what? It's constantly moving back to the left. It's developing higher head on that constant speed as the flow is being reduced. Why is it being reduced? Because the valves are closing, because the set point's being satisfied. So as you move into variable speed, and it became the technology, VFD drives and all of that, and taking induction motor, maybe 60 hertz, 1750, 1800 RPM motors, or 3400 RPM motors, 3600 RPM. You start to apply this thing called the affinity laws, pump affinity laws. And I don't know that we touched on all of these last week, but mathematical relationships that exist that allow you to predict not only the change in flow, but the change in head, and then the required horsepower. If we change either the impeller diameter, which we're not going to do, or change the RPM, which is our speed control. And that's what we're doing with variable speed. We're changing the speed. So the three laws, if you will, the three pieces of information to take away. The pump capacity varies directly. It's a one-to-one relationship as the speed change. So if I have a certain speed, I cut it in half, my flow rate is exactly in half. There's a one-to-one relationship. That's a pump affinity law 1. Number 2 talks about the pump head. That's that part about the varies as the square. So when I change the speed, in this case here, RPMs, it's a squared relationship. So that head drops by a squared, or it increases by a squared as I increase or decrease that speed. And the last one would be the required horsepower. The brake horsepower varies as a cube, which is really why, from an energy savings, that's what drives and has been driving variable speed, and why it makes so much sense for years and years, to the point where nowadays utilities even have some pretty aggressive VFD drive incentives for commercial customers that maybe have some older equipment still out there, pumps or what have you, that don't have a drive. And maybe they're not ready to replace the pump yet, but they can add a drive to that, and the utilities will provide these incentives. So they see the value, they know the value. So in this case here, it's saying it's a cubed relationship. But I change the speed from one to the other, whatever that difference is, cubed, not squared, but cubed times the original required horsepower. So there's where my pretty substantial energy savings can occur. In a nutshell, when you look at all three, and we look at, up above, they're talking diameter, which years ago, it was pretty common. You say, hey, I got this pump, it's way too big, it's oversized, overheaded, blah, blah, blah. Take the impeller out, bring it downstairs. We have a pump shop downstairs here at FIA. We'd put it on a lathe, we'd do some calculations. Okay, what should we trim off the impeller? And now it's going to perform differently. But with today, with variable speed, with drives, hardly ever doing that. We're just putting a drive on it, and we can ramp that drive down. And in changing the speed, it's the same as if you change the diameter of the impeller. You just change the RPMs. So in this case here, 1-to-1 on the flow rate, a squared relationship on the head as you change the speed, and a cubed relationship as you change the speed on the power consumption. So 1-to-1, squared, cubed. Very important. And so here, Willie, how are we doing with our dinner has arrived? Why don't we take a quick break, stretch the legs, grab a quick bite to eat. Everybody that's remote, I'm just going to mute myself. It's 25 past 5. We'll get back together, say at 20 of 6, something like that. So get you out of here by 9 o'clock tonight. Reaction. Everyone's awake. Oh, they just woke up. Wait a minute. All right. So we'll take a quick 15-minute break, and we'll be back with everybody. Will, can you hear me? Yes. Perfect. Okay. So everyone remote, we're going to get back at it just a little bit after 20 of 6. So kind of continuing on with our moving into variable speed pumping. They're just showing a quick example here of, let's see here, of a pump curve. It's constant speed. And what we're showing here is the design conditions that we talked about in our example of that 100 gallons a minute, which is reflected down here on the horizontal curve, and the 100 feet ahead, which again, kind of unusual, but we pick a pump, got a 3450 RPM constant speed motor, and the curve with a 5 1/4 inch impeller. And I cut that flow rate in half, kind of just following along with that pump affinity loss. The relationship or the ratio when I change the speed, how it impacts flow. I could pick the same pump, but just pick it with a 1725 RPM motor and with the same impeller diameter. So I didn't change it, I just changed the speed. I will have a flow rate of 50 gallons a minute and a pressure differential of feet of head of about 25 feet, which kind of falls in line with that pump affinity law of change the speed, the flow rate is a 1-to-1. The relationship on the head loss is a squared. So back here, 100 gallons a minute, 100 feet ahead, cut it in half by cutting the speed in half, 50 gallons a minute flow, and a quarter, 25 feet ahead is the head loss. So same pump, two different motors, just following that pump affinity law. And this is just a kind of a verbiage. You can reference it later on when you get the copy of the PowerPoint presentation. But here what we've done is said, hey, let's go with our pump software and let's select it for variable speed. So one pump, variable speed. And really what you're doing is, instead of having a bunch of different impeller curves on the variable speed, when you're looking at what this represents, you're looking at different speed curves is all it is. It's describing what RPMs we're operating at. And it's really almost infinite from a max to a certain minimum. They're just highlighting, you know, a certain number of them, if you will. So within that same pump, that 3450 RPM at full speed, 100 at 100, as I vary the speed down, maybe respond to system conditions. In this case here, I would cut it. Oops, let's get rid of that. Let's see here. Hide that. Oops. I've reduced that flow by 50% down to 50 gallons a minute. Here's my about 25 feet ahead, just over 20. At that half flow, quarter head loss. And here it is. Here's the curve. 1725 RPM, 3450 RPM. So same pump, change the speed. That's variable speed pumping. All you're doing is changing the speed. And again, we talked about it before, variable speed, what's happening? As I reduce that flow, my pressure drop changes, right? The original we talked about before, the 30 feet ahead, the 10 feet ahead at 100. As I reduce that flow, my pressure drop changes. But I still have that, what they call a control head, if you will, a DP control. So differential pressure set point. In this case, maybe I've picked it at 20, and that's a function, oh, going the wrong way. That's a function of the 10 feet of pressure drop and the 10 feet on the control valve itself. So with the variable speed, with the variable speed here, I have my pump is down to 50 gallons a minute, but now I'm only developing 40 feet ahead at that reduced flow. With the constant speed, originally I had 115 feet ahead. So I had that fixed constant speed. Now I have variable speed. I'll change the RPM. So I'm introducing speed change constantly, and I can bring that pump curve right down to an example of this right here. Maximum 100 at 100, reduce it down. In this case here, what I'm showing is if you look at the pump curve, or the system curve, I guess I should say, or the control curve, you'll notice that it's not going down to 0. It's starting at that control head that I've determined is going to be 20 feet. So my curve starts at 20 feet ahead, because I always want that as my, make sure I have that appropriate pressure drop for that, you know, of the several terminal units, the guy that maybe has the greatest pressure drop, I've determined that to be my control head. So that's my curve, starting from 20 feet, always fixed. And then the variable will be the remaining pressure drop of 80 feet of head to 100, or 80 feet from 20 to up to 100 of head loss changes. Just a visual of that pump affinity laws applied to, in this case here, speed. We're not talking change in the impeller diameter. We're just saying change in speed. What's the change in flow? What's the corresponding change in head loss? And then the third column would be our horsepower required. So cut the flow in half. Head loss is a quarter, and the required horsepower is about 13%. So it's pretty substantial, and that's where the savings comes in. This would have been reflective. Again, it's in one of your manuals, and it was showing the same thing in a graph form that this graph or this table or tablet shows right here. Is you take that 100% of flow rate, you reduce it by about 50% over here. The corresponding head loss is 25%, and the corresponding required horsepower is just under 15. It's about 13%. So ASHRAE highly recommends that any of this, they're almost as restrictive, saying anything with over 2 horsepower, you're going to introduce variable speeds. You guys are doing variable speed all the time. This is what's going on. And obviously this is, again, maybe an older drawing, maybe, but potentially a little more current. What's the difference between these two pictures other than color? Variable primary, and then we're still calling it variable speed, but how are the chillers connected to this system, this distribution system? Yeah, primary, secondary versus maybe variable primary. So I don't have that primary, secondary connection. My primary pump, if you will, is providing flow. In this case, the label is boilers. It could be boilers or chillers. It's the same distribution pumping that's going through all of my terminal units. Back here, it might have been production or a primary for my chillers or boiler plant. And then this is my secondary or my distribution pump that's responding to load changes with some type of variable speed control. And then a third, I think we touched on it the first week briefly, but this is kind of fairly busy, but that would be primary, secondary, tertiary. So I'd have my plant, my chiller plant in this case, perhaps my distribution that's feeding multiple buildings. And then within each building, I have my tertiary pump going to my fan coils or whatever they are, my terminal units within each, building on campus perhaps. And then I have, again, drives for both the distribution that's feeding the buildings depending upon the load of the control valve. And then I might have, as individual terminal control valves are changing or closing, controlling the variable speed of the tertiary pumps. So, it can be a really fairly complex system, a built-up system. And what they're trying to show here is when you're picking the pump, duty point. Duty point just means what's your design condition, what's your flow and head, what are you calculating? And whatever that is, you might pick it just slightly right of best efficiency point, BEP. And the reason for that in variable speed would be you're going to see a lot of a higher percentage of operation. You can still achieve some fairly high pump efficiencies by picking it to the right, because they're not operating out here all the time. They're operating somewhere in this range. So you're still achieving high efficiency with your pump selection, with your pump operation. This was just a quick example of variable speed pumping with parallel. So multiple pumps in parallel. In this case, it's 3. And they're saying, hey, design conditions are such that I'm looking for 3,000 gallons a minute at 50 feet ahead. So 3,000 GPM, 50 feet ahead, and I got 3 pumps in parallel to get there. And so they're showing 3 different curves. They got this kind of tan or cream colored. I apologize, but this blue is supposed to represent the green, and then the red is the red curve here. And I have this minimum control head that's going on out in the system. In this case, it's just under 20 feet. So the curve, the system curve starts not at 0, but just at the base of that minimum control head of maybe 18 feet ahead. So the question is, can a single pump be used? So variable speed with all three pumps running, and that's kind of reflecting how it would operate somewhere on that curve. If I shut off one of the pumps and I only ran two of them and they were in parallel, and I'm changing the speed of both pumps, here's my operational points. And then the final question and example would be, if a single pump was running, could that single pump still achieve certain conditions within that system? And the answer is yes. That curve at 1100 RPMs is still intersecting that system curve, or that really you'd call it that control curve. So it's down near the end, but I could really run about 25% or 750 gallons a minute. So that's not uncommon to do parallel variable speed pumping. When I need it all, I'm out here at that 3,000 gallons a minute. And then as the load changes and valves are closing and I can start backing off pumps, I can do that. That's a common application for variable speed. This is just showing you the variable head loss ratio, depending upon constant head loss versus, so the constant head loss, and sometimes we'll get into some examples, but that control head. And because in the mechanical room, it's going to read a different constant head loss versus if I'm remote out in the building. And how that impacts what the variable head loss will be, depending upon where that constant head loss is. And it's all a function of the pump affinity laws. So variable speed pumping with terminal control head. So design conditions maybe are saying, look, at 500 gallons a minute, 75 feet, duty point. System curve, though, if you notice, isn't starting at 0. It's jumped up. I have a system curve established based on a control head of 20 feet, the minimum pump differential for the terminal units. I build that in. I've selected that. That's that control valve capability. So typically, as that speed takes place, so that speed reduction, these curves take place, and I'm back and I'm following that curve down, I typically don't want to be anything less than 20% of BEP. So depending upon where that 500 falls, I might be operating, down to as low as somewhere around, a little less than 100 GPM relative to the 500 gallons a minute. But I'm always going to be at that 20 feet of head. I always want to provide that control head, they call it. And these are just quick examples of I'm picking a pump to meet those conditions. And in that software, I can pick variable speed or I can pick constant speed. So the curves look different. I have speed, a bunch of different RPMs being selected, and what that control curve or system curve looks like, starting at that 20 feet ahead versus that constant speed. Now I'm changing impeller diameter. So if I have to meet a certain design condition, I'm going to pick a certain impeller diameter. Impeller diameter. It's kind of jumping ahead a little bit, but sometimes you get into, when you're doing variable speed, what are you measuring? DP, differential pressure sensors. Some pump manufacturers or some applications for variable speed might be sensorless is the term they'll use. And instead of having these differential pressure sensors measuring a difference in pressure between supply and return, they might have some algorithms built into the printed circuit boards, the technology, the information, the microprocessor that's on board, and they'll have the pump curve completely mapped out. What is the flow and head, corresponding required horsepower to achieve that set of conditions, and then what the corresponding wattage should be to consume at that horsepower, that flow and head. And so as system conditions change and say you're operating out here on the far right at 0.1 design conditions, and system conditions change and valves close, the first instinct of that pump is to start backing up on the curve. But the speed, the variable speed drive, the logic takes over and says, wait a minute, you're starting to move away from your wattage and your speed. I'm going to back you down, and I'm going to start, and I have this on board. I don't have remote sensors. I just have this technology on board, and that's why they'll refer to it as sensorless variable speed. And it has its place. It's not good for everything and everywhere, but sometimes either limitations or economics come into play. Sensorless variable speed is an option. Accurate money or accuracy. Sometimes it's accuracy. Yeah, as you get into bigger, or sometimes conditions such that they don't even offer that sensorless in those really large, larger flow and head capacities. It has its place. We're going to get into it. We'll get into it a little bit where it does make more sense. I don't need to get into that. Again, just a quick showing a variable volume. All the saying is these are constant speed on my production, my chiller plant. Here's my primary, secondary piping right here. These are my variable volumes, so my variable speed pumps based on flow controls that are opening, or control valves that are opening and closing. So the volume in the secondary or the distribution is going to vary. Applying variable speed control strategies, curve control. They'll call it that factory generated pump performance map, where they have this adjustable speed drive. Maybe it's right on board the pump, and they might be referred to as sensorless. So it's monitoring motor power and torque change. You might have a DP, so differential pressure sensors across the suction and discharge just right at the pump. That's information that can feed back to this adjustable speed drive, this ASD, that's going to influence the operation, the speed of that pump based on system conditions. So these things are set up on commissioning. And then as the system's operating and things change, it reacts and changes the speed of the pump to reduce. At the end of the day, what we're doing is trying to prevent wasting energy. Change the speed, change the electrical consumption. Applications. Just some bullet points. It's not written in stone, but where zones may be equally located, where maybe DDC systems, direct digital control is not present. Maybe I'm retrofitting, I'm going into an existing system, and I don't have the manpower, the labor to run these remote sensors, DP. I might run these onboard sensorless pump applications. And I'll just take, either this measurement of flow and head and speed, or I might do pressure differential. The performance curve. So I have a primary, secondary applications, boilers and chillers. I have my distribution, variable speed, variable volume on my secondary loop. Throwing some examples real quick, and they're saying, look, I have supply piping pressure drop and return pressure drop that equals about 56 feet ahead, 28 supply, 28 return. I have a branch, a control head of 24 feet that I want to maintain. And so I have a secondary pump that's sized for, in this case here, 1,115 gallons a minute at 80 feet ahead. And of that 80 feet ahead, 56 of it is variable as the flow changes, but I always want to maintain that minimum of about 24 feet of control head, control pressure drop. So if I look at that curve of the 1115 at about 80 feet ahead, there's my total design. But in reality, I have a constant pressure drop, that 24 feet, which was this guy up here. It's the pressure drop of the terminal, the control head, the balance valves, 24 feet. I want to maintain that minimum. So I have a variable distribution head loss of 56 feet of head. So you start kind of doing the math and saying, here's that system curve. We talked about it before, system 5, scale 5, I should say, or you can just do that little math equation, but you're plugging in different flow rates saying, hey, here's my design, 1115 at 56 feet. Why aren't I doing 80? Because I want to discount this constant pressure drop on the control head of the terminal unit. I need that all the time. So I plug it in and I say, well, this is what that curve looks like, that variable head loss curve, right? But what hasn't this accounted for, this graph over here? It hasn't accounted for that minimum 24 feet of control head. So in reality, that's what the curve looks like. It's that kind of it's a compilation of both the variable for the distribution, the chillers, the boilers, the pumping, all of that changes, but that control head is a fixed 24 feet. Here's one of those, perhaps it might be a drive and you're saying, hey, what do I need to put in to establish, how do I establish that control curve as opposed to system curve? And all they're saying here is you have a couple different points. Minimum recommended speed by the motor manufacturer, typically 20, 30%. Maybe it's speed required to generate minimum control head, we just talked about. Maybe it's to generate minimum pump flow. Pump manufacturer says, hey, I got a range from maximum to minimum. I got to honor that minimum. Variable primary speed required. Hey, if I have no primary secondary, so I have variable flow through both my chillers or boilers and my terminal units, maybe that minimum flow requirement is going to be my equipment. My chiller manufacturer says, hey, don't go below X. I can vary, but don't go below a certain minimum threshold. So any one of these four could be what establishes that a minimum allowable pump speed when you're setting these conditions, or setting the parameters within the drive. In this case here, we're saying 1115, again, 1115 GPM, 80 feet ahead. In this case, we have variable percentage of 70% and a constant of 30, right? And that's at 56. So here's my range in terms of dropping from 1115 down to 510, and efficiencies are still maintained. Here's my speed reduction, my turn down. But I still have to maintain that minimum. I got to maintain that control head of 24 feet of head. Here's an example which says, hey, I am not putting my pressure differential sensors remote out in the building. In this case here, say that furthest terminal unit, but I'm actually doing it in the mechanical room. Look what happens to my variable head loss versus my constant. If that pressure drop is right here in the mechanical room, I've really limited my range of variable loss. You know, so it happens. Sometimes it's just a real world condition where I can't get the sensors remote. I'm going to use this in the mechanical room, but you're limiting that reduction, how low you can go with that variable speed. And you just want to recognize that. So it's certainly not the preferred. It's an option, but it's not preferred. You're missing out on operational conditions, or benefit, I should say, reduction. So here's a turn down. You know, it's there, but it's not much, and it's because I've established a minimum control head right in the mechanical room. So I've really reduced or increased, really reduced my variable, really increased my constant. You typically don't want to do that. This is just showing, you know, what happens, and it's kind of a follow-up to that picture here. But what happens where if I'm in the mechanical room, here's my distribution pump, and I have A, B, and C. Where do I put that DP sensor? All the way to the end, maybe halfway, or again, back in the mechanical room. And what that impact is on savings, on speed reduction. And then just kind of plugging in some numbers and what the change would be. But, you know, there is a difference between controlling it at A versus B versus C. So if you're looking for the most energy saving, which is typically what a building owner, client, customer wants, I want to stick it out here. I'm going to try to get that as far out into that system so that I have a greater percentage of variable head loss and only a smaller percentage of control head. Just a quick picture showing a couple of, in this case here, some base mounted pumps with some drives, might be in the mechanical room right next to the pumps, but they have a remote feedback sensor that's measuring supply and return. So here's my distribution, here's my discharge off the pump through my triple duty on my supply main going out to the building. Hopefully as far out in the system as I can. I have a supply sensor. I have a sensor on the return that's feeding back to the suction of these pumps. So this is my, hopefully my greater variable head loss that I can take advantage of. So what type of feedback sensors? How many sensors do you need? Where do you locate them? How do you establish that set point for each? What type of sensors? Where do you locate them? Pressure changes. Change the pressure at a single point. If you're doing a heating system, control loop, closed loop, coils, control valves, that's not the application with just a discharge pressure. But if you're doing like a pressure booster package, so a plumbing application, and you get city pressure coming in and you need to boost the incoming pressure for the high-rise building, so you have a discharge pressure. You could use just a simple single point discharge pressure sensor and say, hey, maintain X. As the incoming pressure changes, I'm speeding up or dropping down perhaps my variable speed pressure booster package. That might be an application. This would be all HVAC heating and cooling, differential, change in pressure between 2 points. Temperature, very limited batch process, not a common application. Flow metering, again, not as common. Potable water pressure booster packages, a pressure sensor on the discharge. HVAC heating and cooling, pressure differential. Air temperatures, again, very challenging. Might be on not so much on the water side. Where do I locate it? Like we talked about, mechanical room, 2/3, or remote. Ideally, we want to get it out to that critical circuit, that far-reaching terminal unit. And again, just kind of reiterating, what's the variable? What's the constant? If I can increase the amount of variable, that gives me the greatest amount of speed reduction, which is energy savings. So I have examples. Remote, if I go halfway through, 50-50, it's influencing the constant, so it's reducing my variable. If I go all the way back to the mechanical room, which sometimes happens, I've really reduced that variable and I have a built-in constant that I have to honor. So it's really important where those sensors, that we want to get them remote as best we can. Suggested sensor locations, where do you locate it? Some assumptions, all terminal unit loads change, same ratio. Might be true, might not be. Head loss of the supply and return mains, the distribution mains, are less than the highest branch circuit head loss. All branch circuits have similar loss, no more than 25% difference between them, meaning all the different fan coils that we're using with the control valves. So there's some, kind of little rules of thumb you want to acknowledge relative to sensor location. And this is just getting very specific with your DP, differential pressure readouts, if you will, where your sensors are. What type of measurement? What does it mean? You might be telling the VFD drive, what 4 MA milliamp represents for hertz, etc. That's up to the individual drives. And again, variable 70% versus 30%. Going back, kind of repeating myself there. This is just giving us a quick example here. Here's that 70% variable with a 30%. I'm all the way out in the system. As that pressure, or as those valves close, I can back up, which normally is what I would do if I was a fixed speed. But because I'm variable speed, I'm just changing that speed. I'm reducing the speed. And in doing so, I've reduced that flow and then the required pressure drop, the 54 feet ahead versus the original, 80 feet ahead. I still have that minimum control head out at that remote terminal unit. Let's see here. Doing the same. Actually, yeah, it's the same thing. Let's see here. Where do you locate the sensors? Making the assumption, all terminal units all the way out. 25% more. We want to find that guy we want to find that terminal unit that has the greatest pressure drop, and that's where we'd locate that DP, the two sensors. Sometimes those drives aren't going to be pump mounted. In fact, a lot of times you get into the bigger pumps, they are located, remote, relatively speaking, they're up on a wall, perhaps, to something similar to this. So the drives are right there, near the pump, but up on a wall, and then the DP sensors are remote out in the system. Something else I just want to make you aware of real quickly, new technology coming on the market. It's actually here now. This happens to be Bell & Gossett, and they call it their Hydrovar X. And it's pretty interesting. It's still at the variable speed pump. It's what's a little different is the technology of the motors that they're making themselves. They're an IE5 category, which is becoming like the ultra higher premium or performance versus an IE3 and IE4. This is like kind of the most efficient motor. Maybe, Will, you can speak to that a little bit better, but I know that they don't have magnets on the assisted. That's what, there you go. There's a bunch of terms, right? Oh, okay. Using the same. Yeah. Longevity, life expectancy. Right. Okay. Okay. But it's a drive right on the pump. So you have a pump. In this case here, we're showing an end suction pump. Another option might be an inline, a vertical inline, but either one of them are coming with this motor, this ultra super efficient motor with a drive built in. And then you can add sensors, DP sensors to it. You've got some, they get into, some pretty aggressive speed control, and they'll reference it in their performance charts, these pump curve performance charts, and they'll say high speed, and then they have a family of low speed. And what they're referring to from RPMs, traditionally would say 3,600 and maybe 1,750 or 1,800. They might be a little bit higher, close to 4,000 RPMs on the high speed family, and then reducing it down. And then in the low speed hydraulic performance, it's 2,000 RPMs and below. And so, anyways, it's just there. Sometimes you might hear the expression as you get into this a little bit of over speeding. So we're over speeding the motor for certain applications. But we've just got a lot of technology on board with a super high efficient motor. Initially, they're coming out as a package, so pump, motor, drive, all is one. I think the intent down the road would be, hey, I've got existing pumps out in the field that may be X number of years old. I can take the existing motor that's out there off and just replace the motor with this motor drives, technology, and put it in place with the existing, whether it be that end suction pump or that inline, vertical inline pump, and then have all of this super high efficient motor and variable speed capabilities right on board. So again, it's just more technology trying to improve what's available to that variable speed arena, if you will. But pretty substantial. I mean, I think it maxes out, Will, if I'm not mistaken, I think it's around 30 horsepower on the high side. 3 to 30, okay. which is what we want to jump into next, to be quite honest with you, is just kind of finish off with ECM. Oop, I didn't want to do that. Maybe I did. Let's see here. Right here. Real quick. Oops. Go back. Get out. Oh, here. Share screen. Will, can you see that on the screen now? Not yet. All right. Okay. You can see it now? Okay. So last part of tonight's presentation is just talking about that. Will it really kind of cut right to it? The 3 horse to 30 horse, some of that other technology. As you get past that 30 horse and you're into 50, 100, 200 horse, massive. Now you're getting into these, drives, probably wall mounted and all of that. As you work backwards the other way, this kind of family fits into that up to 3 horsepower or under. Same thing, pumps coming with, has the motor and the drive on board, mounted on board. So it's got some, it's a printed circuit board. It's a microprocessor on board. It's got some intelligence, and it has its place. It's not the be all and end all, but when you're in that flow rate, BTU, chilled water, hot water capacity, or boiler plant, this has a nice little application. It fits perfectly, and it provides you with that either speed change or different applications. Let's see here. Close that down. Let's see. So all they're showing here is single phase and 3-phase. Bigger. I'm assuming a little more area. We want to get rid of the heat. We want to make sure that this thing doesn't overheat. So we got a little more technology on the 3-phase. We got a little more fins or grooves to allow some airflow to remove or dissipate that heat on the 3-phase units. So real quickly, electronically commutated magnetic, ECM. That's all it stands for, the 3 letters. Permanent magnet on the rotor. These magnets here. Eliminates the need for input power to magnetize the rotor. The magnet's already there. It's attached to the rotor. Motor is microprocessor controlled. Hence, you'll hear the expression smart pumps. So they have some intelligence on board. And then the last part here is this. Power is pulsed on and off electronically. Electronically commutated. So as it's pulsed on and off electronically to create the magnetic field, the process is known or called commutation. Electronically commutated magnetic motor. So it's a very simple drawing, but what it's trying to show here is the green represents the north, the red represents the south pole. This is my rotor, there's my magnets. That would be kind of this picture here, a rotor with the magnets attached. As I electronically pulse power on and off, and that's what we're saying down here, power is pulsed on and off electronically to create the magnetic field in the stator. The rotor, the magnets on the rotor react. So opposites. So the faster these are pulsed on and off, the faster the rotor spins. What's attached to the rotor? The impeller. What's influencing the flow in the head? The impeller inside the volute. As you go the opposite way and you pulse it and slow it down, it slows down the pump, which means the GPM and the feet ahead. So you're reducing or increasing your energy consumption based on the operation, the speed of the pump. And that speed of the pump can be influenced by a lot of different things within the system that you install these pumps into. So it's pretty intelligent. Like I said, in its place, up to 3 horsepower. Onboard drive with a PCB, printed circuit board. Has some operational modes. right on board. So one pump can fit different applications. So you're not picking different pumps or different sensors and all of that. All you do is say, hey, for this installation, I want you to do this. For another installation right over here, I'm going to pick a different mode, perhaps. It's the same pump. So it's pretty flexible. So one very popular out in the apartment, condo, multiple zones with thermostats and a zone valve of some sort is a mode called proportional pressure. And all it's saying is I've got this one distribution pump that's feeding 30 apartments, 50 apartments, coils, baseboard, whatever they are. And same thing as we just talked about the variable speed in those larger applications. This is a variable speed application. As those zones, as those loads change, valves open and close, the pump can respond accordingly. And where the utilities get want or are interested in funding some incentive is I've got speed control. As I reduce the speed, I reduce the kW, the amount of energy this pump is using to heat or cool that space. And it's all happening right on board simply by selecting this mode and kind of dialing a set of conditions. So all we're trying to show here is, okay, what is a proportional? What does that look like when you have a primary pump in a hydronic system and it's using zone valve? Well, it could be a lot of different things. These just happen to be non-electric valves as opposed to electric, but they could be electric. It doesn't matter. But it's a two-pipe system feeding terminal units. And those terminal units, so that they don't only overheat the space, they have a valve that closes. Pretty simple, pretty straightforward. This would be an exploded view of a non-electric where there's no wires. It's just sensing. This is popular in like dormitories, maybe apartment buildings where they don't want to run thermostat and wire and electricity. It's just a self-contained non-electric valve. What I want to show in this drawing here, this little screen here, is what's going on in that proportional pressure mode. So from the drawing on the right here, here's my mechanical system. I got a boiler, I have a distribution pump, and I have 4 terminal units. Pretty simple. What I have over here is the pump curve that's selected to operate in proportional pressure. So all it's saying here is with all 4 of these zone valves open, maybe I'm operating on curve 3. And what will happen is as one of those zones closes, what the pump would normally do is he'd want to back up on the curve like we talked about earlier on a constant speed. But because he has all of the performance points, flow, wattage, RPMs mapped in that software, as it starts to move, he says, wait a minute, you're moving off of that curve 3, set of conditions. I'm not going to let you back up. What I'm going to do is I'm going to reduce your speed. I'm going to reduce that electronically pulsing to reduce the RPMs, which reduces the kW, and I'm going to fall back down on this proportional curve. And as more zones are close, go the other way, I continue backing down that curve. That's all it's doing. So during the course of the heating season, times how many heating seasons, this logic is just constantly changing, opening and closing valves, speeding up, speeding down, slowing down, all the while as effectively as possible reducing energy consumption. So it's a very popular light commercial application. I don't need to get into that. What I just want to show you real quick, 2 curves I'm going to show you. One right here is a particular model number. It doesn't mean anything to us right now, but it's a pump curve. And at maximum curve, here's my maximum speed curve. Here's my set of conditions, maybe at operation. And then I have these various other curves, these speed curves. And what I'm showing here is in proportional pressure, as the valves close and I need less flow, this is the curve I'm going to follow. The pump is going to follow in reducing its performance based on speed control as the system conditions require less and less and less. And you look at it and say, okay, well, whatever. Here's the interesting part. This is where the people that pay the electric bill are interested. is same pump, but now it's a power consumption, a watt consumption curve. So for this curve, as I start to slow down the speed, as I ramp through these various speed RPM curves, look at my wattage consumption. It's pretty substantial. It's a drop. And that's the benefit to that building owner or that person paying that utility bill. It's a benefit to why the utilities say, hey, with this technology, we're going to offer an incentive to upgrade your maybe on-off traditional pump that's been there 1.5 horse, 2 horse in an apartment building, whatever, to go to this technology. Here's the reason. Another application on that same pump is I can do a constant speed, but you can dial it in. You know, just buying a pump off the shelf, you can actually configure the pump curve. What's a constant speed? Something where you have a pump running whenever there's a call for cooling or heating, and there's no zone valves. It's a fixed load. Whenever that turns on, that's what it is. But I can configure, I can dial in that pump's performance to the application, to the terminal unit. So there's a quick example out in the field where I might have a couple of pumps going out to 24, 36 apartments upstairs. Right beside it, I have 2 pumps, one standby, one's, in operation. And maybe it's feeding the domestic hot water production down in the basement. And I'll say, hey, I can put a pump and I can dial in exactly what the manufacturer of these domestic hot water tanks say I need to get my maximum performance. And I'll do that. So right here, I have basically the same pumps, but I'm using them in different modes by simply selecting as I turn the pump on, what's my mode? I want to do proportional pressure for all the zone valves upstairs. I want to do a constant speed for these domestic tanks right here. Constant pressure is another, it's another mode. Night setback, just taking that energy efficiency, they'll represent it by having a moon. If the onboard temperature sensor in the pump senses a substantial drop in temperature, indicating night setback, he says, hey, I'm going to even take that speed control and drop it even further. Another interesting capability or possibility, and that's what these pictures back here were showing real quickly, is there are 2 pumps in parallel. So these pumps have, again, intelligence. They can talk to each other. So I can put them in parallel. I can have one as 100% operation, and I can have one as a standby. Oops, back up. I can have one as a standby, and they talk. And then I have different modes of parallel operation. One of them is just straight backup. One runs, one's backup. Something happens, the one that's supposed to be running fails, backup turns on. That's one mode. I could have alternate, which makes a hell of a lot more sense. And that says one runs, one's backup. But every 24 hours, you change who's the guy running, so I have equal runtime, equal wear. Here, where you get a little more creative, but as the guys become a little more familiar with, get educated, I can have parallel, like we talked about that example of 2 pumps in parallel, and you get half the flow at design head, turn them both on, and I can have additional capacity. You get into some of these pumps, and they're 300 gallons, 350 gallons a minute, one pump. What's the BTUs of 300 gallons a minute? It's been a long day, and you guys are exhausted, so I'm going to answer it for you. But a quick answer would be, hey, George, that depends on the delta T, right? That's the quick answer. So say I did a heating system, I said 20-degree delta T, 300 GPM, that's 3 million BTUs. That's a pretty good sized plant. If I put 2 of them in parallel, I get 600 gallons a minute. I got 6 million BTUs with 2 of these pumps that are sitting downstairs that are very configurable, so it's not limited to really small. You could get pretty aggressive. The point with this technology and this smart is I have automatic parallel. I run them together, but I have the ability, both pumps run simultaneously at the same set point. But as the load changes, why? Conditions change, valves start to close. I don't need all of this. The lead pump starts and stops the second pump. So I can take that and say, hey, we're running together at this set point. The conditions have got to the point where I'm pretty confident I can turn you off and I'll take care of the load. Now, as the load starts to come back online, more zones are calling. Okay, I'll bring it back on. We'll run in parallel. So there's a lot of intelligence with just these, fairly simple 3 horse and under pumps. Just some examples out in the field. What the contractors, the pipe fitters, when they put this stuff in, they like this type of feedback. They can actually, there's digital displays on these pumps. So they let the contractor or troubleshooter, or if we're out there in the field helping set up or troubleshoot, we see what's going on. We got flow rate, we got feet of head, and we have RPMs. So we can see what's going on. And anyway, so there's a little bit of information going on. Temperature is another mode, temperature dependent. In the pump itself, in the dry section, but it's right behind the impeller, there's a built-in temperature sensor. So if you add an external sensor, you could do delta T temperature control, another option. So it could be this guy right here, delta T. Onboard temperature sensor, and then the remote, and I can do supply return. It's an option. One last thing that this thing we take advantage of all the time is it has the ability to receive an external, in this case, analog input, 0 to 10 volts DC or 4 to 20 milliamp input. And it becomes speed control. Very specifically, it's for boilers. I get into some big BTU condensing boilers that can modulate their firing rate. So at 100% fire, I want 100% flow across that heat exchanger. But as the building system conditions change and the modulation starts to reduce, why? Because I want to save gas consumption because the load's not that great. In parallel, why don't I save the flow rate across that heat exchanger? Instead of keeping it full flow with a reduced modulation, I have now technology that can respond to that. So I have onboard smart that can take this 0 to 10 or 4 to 20. So I just want to jump to a real quick. Here's the issue. When you're into high efficiency boilers, condensing, modulating boilers, one of the things that can really impact that efficiency point is the return water temperature, right? And if you ever have a scenario where I am in my boiler plant, I'm taking some hot boiler water and I'm actually not sending it out to the system, but I'm bringing it back into the return. And that can happen when I do fixed speed boiler pumps instead of variable speed. If I do fixed speed and the load out here says, hey, I only need X, some of that hot boiler water goes right back to the return. What does it do to the return temperature? Elevates it. And as it elevates it, look what it does to the efficiency of that boiler plant. It can start to reduce. So you start to, the building owner, the guy paying the bill, starts to lose some of the potential energy savings. So by putting on variable speed, Jesus, I can't even speak here at the end of the day, variable speed pump, I can now maintain a fixed delta T across my heat exchanger by changing the flow rate through the boiler to match the firing rate of the boiler. So these boilers, these high efficiency boilers, have intelligence on board that they'll send out a 0 to 10 or a 4 to 20, and they'll be looking at their sensor right here at the inlet of the heat exchanger and the sensor right here on the outlet. And if you dial in and say, hey, maintain a 20-degree delta T, as it modulates down and you're over pumping, that delta T gets tighter. So slow the pump down so you increase that delta T back to your desired 20 degrees. So that's another very popular and very important or favorable. So in all of our high efficiency boiler plants where these pumps fit, that 3 horsepower and under, they're putting these boiler pumps in that can now talk to the intelligence on board to vary that firing rate and to vary that flow rate to match. We don't need to go into some examples here. One last thing, just to be aware of, you might have already heard of it. But as you adopt this technology, ECM, you're bringing these magnets in the pumps into your hydronic systems, which is all good. But over here on the East Coast, we have a lot of existing systems. If we're upgrading mechanical rooms, but we're attaching them to existing buildings, there's a chance that there might be some iron oxide, steel pipe, steel terminal units, iron oxide floating around in the system. Well, a magnet does a very good job of being a magnet. So if I have iron filings floating around, I need to protect my investment. My point is I'm leading up to some type of magnetic filtration. So in this case here, I'm showing a boiler mag. There are other manufacturers out there we just happen to represent, but it's not going to be uncommon on these high efficiency upgrades to not only go with the high efficiency condensing plant and the high efficiency pumping capabilities, the third leg is some type of filtration, magnetic filtration. And these pictures, which are kind of ugly, is they're showing in a very short period of time, these magnets that are crystal stainless steel clean, how much filtration, how much iron oxides are floating around in the system. And if you didn't have this filter, it would show up at the pump. Because on the back side of that impeller, that's the wet part, is this magnet. And the magnet, and all of a sudden the pumps go to turn on and they've got all this iron filings that start to build up around the impeller. So it's just become common practice as this new technology is not that new anymore, but it's out in the field. You might be also specifying some type of magnetic filtration to pick up any of the sediments that are out in that system. It's very good practice, design practice. Then these are just different pictures of what it looked like. But this, you put this in, here it is crystal stainless steel clear, this magnet, and then they're taking it out after X number of hours, X number of days, whatever that sequence is of all of the filings that they grabbed, which is good. That's doing its job. And with that, see you next week. Thank you very, very much for coming. Thank you, everybody remote, for hanging in there. And we'll see you next time, next Thursday at 4 o'clock. So hopefully everyone has a good night, a good week. Go Celtics, go Bruins if you have any interest. Hopefully the Bruins show up next game a little better than last night. Yeah, they got spanked last night. But anyways, thank you all. I appreciate your time.
Thank you.
Yeah, there you go. For all of our remote, as well as everyone in the classroom, David will be posting the PDFs for this week's PowerPoints or sending on an email so you'll be able to access them and save them. So again, we appreciate your time. Thank you.